Hey guys, in this video we're going to be taking a look at how to calculate the magnetic field strength of produced from a current going through a wire. So if you have a current, well conventional current going through a wire, so let's say this is some current with some amps, a magnetic field will be produced around the wire. Now the way you work this out is basically we're going to use one of the things called our right hand rule. So a right hand rule is pretty much going to determine the direction of the magnetic field. So right hand rule that we'll be using will pretty much be, alright, if you have a current, and if it's conventional current, so the flow of positive, you point your thumb in the direction of it, and then you wrap your fingers around the wire. So for example, I'm going to try and draw a hand as best as I can. This is terrible. But pretty much all you got to do is stick your thumb in the direction of pretty much the current. So it has to be conventional current, they have to specify this, and wrap your fingers around it. And your fingers will show you the direction of the magnetic field. Okay, so that will pretty much show you a direction. Now the way you can calculate the magnetic field strength is using this formula here. So B equals mu sub 0 of I on 2 pi r. Now you're probably wondering what each of these terms mean. Well, B represents our magnetic field strength. So that's measured, its units are Tesla. So I'll just put a big T there for Tesla. I is the current, it's measured in amps. And mu sub 0 is pretty much just a constant. So that's the permeability of free space. So off the top of my head, I think it's 4 pi times 10 to the negative 7. Okay, and r in this case is distance. So what this means is if we have a current and you have some distance away from it, you can work out the magnetic field strength there, because we know the magnetic field is going to be going around here like this in a loop, but it's going to get weaker the further away it is. Alright, so let's take a look at a specific question that deals with this. So there'll be two parts to this question. One, we'll have to work out the direction of the magnetic field, whether it's going around like this. Now if the wire was going this way, it would be the opposite way, so it'd be like going this way. So you have to use your right hand rule. So you need to stick your right thumb in the direction, and then wherever your fingers curl will be the direction of the magnetic field. Oh wait, this one. So stick your right hand and then wrap your fingers around, so you'll be going like this. Yeah. Right. This one's incorrect. Stick your fingers, it will be going this way. Awesome. Alright, so I was just fixing those up. I did it wrong with my right hand rules. Okay. So let's take a look at a specific question. So the question is you just have a current in a wire, and the current is, let's say, 12 amps, and you want to work out the magnetic field strength a distance of 6 centimeters from the wire. Now mind you, this distance needs to be in SI units, so meters. So if you want to have a go at this question, feel free to pause the video and have a crack. Alright, so this is the formula we're given. So B equals mu sub 0 of I 2 pi r. Okay, r in this case is 6 centimeters, so that's going to be 0.06 meters, because you need to divide by 100 because you have to put it in meters. Mu sub 0 is just a constant, so that's just going to be 4 pi times 10 to the negative 7. I is going to be 12 amps. Okay. The units for this, I think it's newtons on a squared, if you wanted to know the units, but I'm going to leave the units out because it's just going to get cluttered up. Alright, we got that, we got that, we got that. We can just plug in because we got to find what B is. So B is going to be 4 pi times 10 to the negative 7 times by 12 all over 2 pi times by 0.06. Okay, you can plug that into your calculator, so I'll just do that now. So we'll have 4 shift pi times 10 to the negative 7 times 12 over, and you should get 4 times 10 to the negative 5 Tesla. That should be the strength of the magnetic field at this point. Now let's work out the directions. So stick your right thumb in the direction of the magnetic field, and your fingers should wrap around. Oh, that's a terrible drawing, sorry. Your fingers should wrap around like so. This is a terrible drawing. So the magnetic field will be going around like this. This is a better drawing, so I'll just draw the field lines. So it should be going around like that. Okay? Right. It's a pretty easy, the math is pretty easy. The direction stuff is probably the hardest part. But once you get used to it with the right hand rules, it becomes really easy. Okay. Now let's take a look at the net strength of magnetic field. So these questions here are pretty easy when you have one wire. But what if you had two? Because if you have two, that means two magnetic fields are produced. So let's say we had this situation here. So you had this wire that went in this direction with conventional current of 5.5 amps. And let's say you had this wire here that went in this direction with 5.6 amps. And let's say we want to work at the magnetic field strength, the net, at this point here. And this is, let's say, 25 centimeters from here. And let's say this is 26 centimeters. All right. Well, first of all, we need to work out whether the magnetic field from, let's say, wire A will cancel out or add with wire B. The reason for this is because if they're going in different directions, like let's say if we have two magnetic fields, like let's say we just had, I'll just draw a magnetic field. Let's say a magnetic field like this and a magnetic field like this going in the opposite direction. At some point here, if I move them close enough together, they'll be going in the opposite direction, so it'll effectively cancel out there. But if you had two magnetic fields going in the same direction, so for example they're like this, and they were put close together, they would add together, they wouldn't cancel out, if that makes sense. So here we've got to work out whether we've got to cancel out or we've got to add them together. So the way we do that is work at the direction. So let's work out for YA. So stick your right thumb in the direction of the current and wrap your fingers around. So you'll find it goes around like this. Right. Okay, so now I'm going to introduce you to another concept of notation. So the way we indicate, like, obviously this is like a 3D thing, so the way we indicate going into the page, so if it's like going into the page, we indicate it with X's. The reason for this is because it represents, if you were looking at an arrow getting shot away from you, you would see the back of the arrow looking like this. If it's going out of the page or towards you, we draw dots, because if you were to see an arrow coming at you, you would just see the little dot. So the way we would represent this effectively is, alright, this side here, this is going into the page, isn't it? And here, it's going out of the page, towards you. So rather than drawing these horrible little circles, all we got to do is draw these dots and X's, okay? Okay. Alright, so now we can get rid of those. We can still have one little circle just so we have the an artistic drawing of it, but this is all we pretty much need. So this diagram tells me, alright, looking at from this perspective, the magnetic field is coming towards me on this side here, and it's going away from me on this side. So that indicates it's doing something like this. Alright. Okay, so let's take a look at wire B now. So wire B, stick your thumb in the direction of the current and wrap your fingers around it. So it will be going into the page on this side and towards you on this side. Right, so we have the situation where both of these are in the same direction. So instead of cancelling out the magnetic fields, each magnetic field will add to one another. Okay. So the net magnetic field we know at this point here is going to be into the page. Right. So now we know the direction, it's going to be into the page. Let's work out the actual calculation. So we'll just need our formula like we found before. B equals mu sub 0 I 2 pi r. So let's work it out for A. So A, our current, what was our current? 5.5. So just recall mu sub 0 is 4 pi times 10 to the negative 7. So B equals 4 pi times 10 to the negative 7 times by 5.5 all over 2 pi. And don't forget to change this to meters, so it's going to be 0.25. Plug that into your calculator. It should give you that magnetic field strength from wire A. Okay? 4 shift pi times 10 to the negative 7 times 5.5 shift pi 0.25. Okay, so I got 4.4 times 10 to the negative 6 Tesla. Okay, and that's going to be going into the page. It will be in the same direction as this. So this is for wire A. Now let's work it out for wire B. So wire B, same stuff as before. 4 pi times 10 to the negative 7, except you got to use this current now, so 5.6 all over 2 pi, and don't forget to change this distance to meters, 0.26. Okay, plugging that into your calculator, it's only going to be slightly stronger because, well, actually it might be the same because this is further away by 1 centimeter, but it is a stronger current slightly. So we'll have to see which one is stronger or if they're actually the same strength. 0.26. Alright, so this one's slightly weaker. The reason why is because it is further away. So the bigger the distance, it's going to make a huger impact because the current's only increased by 0.1. So this is going to be 4.3 times 10 to the negative 6. So hopefully that makes sense why this magnetic field strength from wire A is a lot stronger. Because while this current isn't as big as this one, is only a 0.1 of a difference in amps. But it's closest to this one here, so this distance here is going to make more of an impact. If this was like 6 amps, then this wire would be more dominant, and this number that we calculate here would be bigger than this one. But this one's more dominant because of the reason I've just stated there, about the distance. Okay, so that's all good and great. We've calculated the net magnetic field for each wire. Now we got to work out the field at that particular point. So since they're both going into the page, so since both magnetic fields are hence like doing something like this is going to be a terrible drawing. It's going like this. They're both going inward. So you see how these two bits here, actually I'll use a highlighter to better demonstrate that. So you see how both these things are going into the page here, meaning they're going to add together. They're not going to cancel each other out relatively. So all you got to do is just add these two numbers together. So 4.4 plus 4.3 times 10 to the negative 6. That's it. 4.4 plus 4.3. 8.7 times 10 to the negative 6 Tesla. That will be the net magnetic field strength at this particular point here. Now let's take a look at another example where they don't add together. So let's take a look if they had this situation here. So let's have two wires again. And let's say one's going, let's say they're both going in the same direction this time. But this one has a strength of 5.6 amps, so similar to the wire B up there. And this one has a strength of, let's say, 8 amps. Okay, but let's say this distance here is 27 centimeters. And let's say this distance here is 23 centimeters. Okay. We want to work out the net magnetic field strength at this point, let's say Q. Okay, so how do we do it? So we've got to work out whether we're going to have a situation that cancels out, whether it cancels out at this point or adds together. So effectively we want to know if we've got this situation with the magnetic field or if we have this situation. If they're going with each other, they're going to add. If they're going against each other, they're going to cancel each other out, so it'll be like a difference. Okay, so let's work out the direction of, let's say, the wire A. So I'll label this A and this B. So wire A, stick your thumb in the direction of the conventional current, so I'm assuming this is conventional current, and then wrap your fingers around it. So the fingers will be going towards me on this side here, and will be going into the page on this side here. So effectively we have this situation here. Hopefully that makes sense with your right hand rule. If you don't, just go back to the start of the video where I was talking about here. So stick your thumb in the direction of the current and wrap your fingers around, and it will show you the loop of the magnetic field. Okay, so that's for wire A. Let's take a look at wire B. Now, wire B is going in the same direction as wire A, hence due to the arrow. So that means it will go towards you on this side and away from you on this side. Now you can double check that with your right hand rule as well, but you can just work that out from having parallel lines there. Now, what this means is we have a difference in here. This is not the same. This is going into the page, and this is going out of the page. What that means is the magnetic field strength of wire A and the magnetic field strength of wire B are going to cancel each other out at some point here because they'll be going against each other. So we need to work out which one's more dominant. So we have to now do our calculations. So all we're going to need is our formula again. So B equals mu sub 0 I 2 pi r. Okay? So let's work it out for wire A. So wire A, B equals mu sub 0 I 2 pi r. So what we have here is 5.6. So 4 pi times 10 to the negative 7 times, what was it? 5.6 all over 2 pi. And don't forget to change this distance to meters. So that's going to be 0.23. Plugging that into the calculator. 4 shift pi times 5.6. And I get 4.87 times 10 to the negative 6 Tesla. Okay, and this, now we go indicate our direction. So at this point here, from wire A, it will be going into the page. So at this point here, from this perspective, it's going to be going like this from this wire here. This one here, it will be going in the opposite direction. It will be going like this. So let's take a look at the calculation for wire B. So that's wire A. Wire B, same formula. B. So we have 4 pi times 10 to the negative 7. Now the amps for this one, this is a stronger current here, but still conventional, so we can still use it. Why don't I put the A? I try not to keep the units in my calculations. I kind of put them afterwards. Divide by 2 pi, and that distance there is 27. Don't forget to put that in meters for SI units. 0.27. Plugging that into the calculator, 4 shift pi times 10 to the negative 7 times 8 divided by 2 pi on 0.27. Okay, so I got 5.925 times 10 to the negative 6 Tesla. Now I'm going to round that real quick, so I'm going to have that as 5.93. Okay, now let's take a look why wire B is more dominant. So this is going to be out of the page. Even though point Q is closer to wire B, or wire A, this here is got such stronger current, so the magnetic field is going to be a lot stronger. Even though it's further away, because it's like at least 2.4 amps higher, it's going to be more dominant, even though this distance is small. Even though this one is 4 centimeters further away, because of the current strength, it will be more dominant. So what that means is, at this point here, the magnetic field strength will be going out of the page because this number is larger than this one. So our net magnetic field strength at that point will be this number subtracted this number. So that's going to be 5.93 minus 4.87 times 10 to the negative 6 Tesla. Okay, so that'll be 5.93 minus 4.87. So 1.06 times 10 to the negative 6 Tesla out of the page. So at that point there, it doesn't have a lot of magnetic field strength, but that's only because this magnetic field is cancelling out with this one here. If you had them as the same distance and you had them as the same current, there would be a point halfway where there's no magnetic field strength at all. Righto. Hopefully you guys enjoyed that video on magnetic field strength. Yeah, there'll be more coming very shortly. Yeah, all good.